Well, g'day, it's Mr. D here on the RV Investigator, and we're going to interview Michal, who's been doing some seismic work. So we want to find out a little bit more about seismic. So let's go and chat to Michal, who's the one that's sort of in charge of interpreting all the squiggles on the page for the seismic sort of stuff. Well, Michal, it's Michal, isn't it? Was just looking at this because we've done a little. This students can download as well. Michael, it says there. That's how I would read it, but obviously it's pronounced differently.
Yeah, it's a bit of a funny pronunciation. It's what people are used to. The L actually isn't in the English alphabet. It's got a little line through it. It's called an L.
So where's it from?
Polish.
It's Polish?
Yeah.
All right, excellent. Now we want to try and understand some of the stuff that you've been doing. So we know that everywhere the RV Investigator goes, it maps the sea floor. So it does that with bathymetry. So it's sort of like a sonar type thing that maps the depth of the ocean. But you do something a bit more different, that you can actually see below the ocean floor somehow.
Yes. Well, just like bats are good at seeing in the dark by using echolocation, they send out a sound and it reflects back. That's at a high frequency, so a very high-pitched sound. Bathymetry uses the same high frequencies to have a very detailed map of the seafloor.
Mm-hmm.
But if we turn that frequency down and get the sound lower, the lower it goes, the more penetration we can actually go into the ground, and use the same technique of echolocation to map different layers within the Earth.
So sound travels through the water as well as travelling through the rock, is that right? Or?
That's right. When it travels through the water, it's an acoustic wave.
Mm-hmm.
Transmits into the ground, it's a seismic wave. The same kind of wave, just a different name.
All right. So, so something to do with how that sound travels and how it returns. So what we've seen, or we might even be able to put a picture on here somewhere, is that you've got some equipment that you put in the water, and that equipment puts in a sound, and then there's this big long trail of something called a, what's that called, that trail that you've got, the receivers of some sort?
Yes, the hydrophone streamer.
And then that picks up the sound in various locations.
Yes, so it'll, each receiver will image the same location on the seabed and the subsurface.
Uh-huh.
And the idea is then to stack those recordings so we can boost that signal of the events that actually are real reflectors and subdue the noise that is dissipated through negative interference.
Right, well I don't know if I really understood a lot of that, but I'm going to have a look at this quick picture.
Yeah.
Because this is the bathymetry, this one here. And so what they did here is they mapped a region. Which one are we looking at, you actually showing us today?
Okay, so we're looking at a seismic line through this bathymetry here.
Okay, so this is the ocean floor here, and then you've put some sound waves down there so that we can see underneath the ocean floor.
That's right, so our ship track, we've been travelling along this white line here, and the seismic line I've got is from about this area here, which is a slight bathymetric elevation.
Yep.
And that dips down, we come to a ridge in the middle, which is an elevation and on the seafloor, and we continue along where there's a few subtle ridges and then start coming up on this seamount plateau.
And so on the screen here, you've sort of got, I'll just do the screen first, this is sort of looking down below and there's a lot of squiggly lines. So how does the seismic go down and work that out?
So each of these coloured lines is a reflector. The colour denotes whether it's a positive or a negative amplitude phase. So if you think of your sinusoidal...
So sort of like a like a line that looks like a sound wave or just a normal water wave. You've got the top part and the lower part, the maximum
right.
and the minima. Yep.
Yeah, that's it, maximum and minima. And this is your seabed.
Yep.
Which is the
first
reflector.
I can see that.
Yeah, we've got all water column here, so we don't have any geologic information really in there. And we're looking at sedimentary layers.
Yeah, man, that's great, isn't it?
Yes.
How deep is that?
That thickness is getting close to 2 kilometres.
Wow.
Yeah.
So each of those layers is some sort of sedimentary rock layer.
That's right.
And then as we go up here, we can see that, you know, there's some other little bumpy bits as well. So what can you tell about the types of rocks?
Well, hard rocks tend to dissipate and scatter the signal, so we lose a lot of energy. And soft rocks allow that energy to transmit for a longer depth.
Yep.
So what we're seeing here is a lot of soft sediment reflectors and then this hard amplitude or high amplitude
Yeah.
boundary, then we can make an assumption about the compressibility of that material. So we call that hard rock.
Yep.
And we can trace that along and map it, and it's actually structurally disrupted in places. So we can start to see that there's some structural complexity.
So some faults or something like that in the
Yes,
rock.
some faulting with soft sediment that's been draped on the top of it.
Now, one of the things you were telling me before is that the speed of sound is faster in water than it is in air,
Yes,
and it's faster in rock than
again,
it is in water.
that's right.
And different rocks.
Yes, different rocks do have different velocities. So a rough way of, or a rough guide would be the harder the rock, the faster the sound will travel through it.
Right. Okay. And now you've printed this out for us.
Yes, so we have a seismic profile here, which is looking at this part of this section of the bathymetry.
Just hang on a second. We've got they're actually putting the dredge back down again, so we've got the radio sort of happening here at the moment in the background. Excellent. So they're putting the dredge back in again, aren't they? We've just picked up some rocks.
Good news.
Yeah. So what we've been doing is we've do the seismology there, and then we pick a site and we put the dredge down and drag up some rocks just to confirm things. This is really good. So this is that. Do you want to just explain that?
So we're looking, this section from left to right is looking south to north, and we're looking approximately in this part of the bathymetry here, and it's subsurface information.
Right. Yeah, and you can actually see the ridge.
Yeah. So as we're coming along this side, we're tracing the seafloor. There's a ridge here in the bathymetry, and we can see that in the seismic data coming up here.
Yep.
And that continues through this depression, which is a sedimentary basin.
Yep.
And then we come back up on a subtle ridge. That goes down again, and then we come up again on this larger seamount plateau.
Wow. And we can see that purple area there on this map, which looks fairly flat, underneath is actually a whole lot of sediments that have filled a valley of some sort.
Yeah. So that those sediments have flattened off the topography, which otherwise would be very irregular.
Wow. Well, that's amazing, isn't it? You can see all that, and that's actually quite deep. How deep in the water was that?
Oh, we're mapping ranging from about 4.5 to 1.5 kilometres deep.
Right. So from 1.5 kilometres deep to 4.5 kilometres of water, and then down, and then you get a couple of kilometres into the.
Yeah, and then a couple of kilometres into the earth itself.
Oh. Oh, that's really, really interesting stuff. You must enjoy your job.
Oh, yeah, absolutely love it.
Awesome. Thanks very much, Michal.
No worries.